On July 28, 1976, a 7.5 magnitude earthquake struck Tangshan, China, and decimated the city and its coal mining industry. Official reports claim that 242,000 people died, but estimates are as high as 655,000. Most of these fatalities resulted from the collapse of unreinforced masonry homes, where people were sleeping and which were not fixed to the bedrock. The deep, sandy soil in the city turned into a fluid-like mass, destroying and unsettling homes, multi-story buildings, and other structures. Cars, crops, buildings, and people fell victim to a phenomenon called soil liquefaction, a devastating phenomenon that can occur during earthquakes. Quicksand is the most well-known instance of soil liquefaction. It is when the soil essentially becomes a thick, viscous liquid so that, instead of resting on top of the soil like normal, objects sink, or more precisely, they float on the soil. But this doesn't just happen in movies, it happens all over the world, and is a huge concern in earthquake-prone regions such as Alaska, China, Ecuador, and Japan. Cars can be swallowed by the soil when it loses its strength, or once sturdy buildings can fall over and be destroyed.
Soil liquefaction happens when three conditions are met. The soil is saturated or partially saturated, the soil is loose and sandy, the soil loses a part of its strength because of the changes in the stress in the soil and the forces acting on it. Saturated means the soil has as much water in it as it can hold, and you can visualize this with a jar, some ping pong balls, and other plastic objects, and some water. The ping pong balls represent the soil particles. When you put the water in the jar, it fills all the pores and the empty space between the balls, making them saturated. Another point to note is the ping pong balls rest on each other. The weight of the balls create a force on top that acts on the balls in the bottom of the jar, called effective stress, and that keeps all the balls in place. Effective stress is also what gives the soil its strength, keeps it in place, and is what supports cars, buildings, and you. If the soil is loose and sandy, that means it can be compacted into a smaller volume. When the soil is compacted by something like a weight, the pores get smaller and the water pressure between the soil grains increases. The water flows out of the pores to a place that has lower pressure. The same thing happens during an earthquake. However, soil is loaded so quickly during an earthquake that the water has no time to flow anywhere. The pore water pressure increases and pushes the soil particles apart until the soil doesn't have the strength to support whatever is resting on it. So you can see in our jar that the pressure acting on the balls exceeds the effective stress between them, making them float.
Now let's show soil liquefaction in action. Here's what you'll need. 4 equally sized round balls, a shoebox-sized container, a watering can, an item to represent a building, and sandy soil. Once you've gathered all the materials, you can begin to set up your experiment. Fill the container about 2/3 full of sandy soil. Slowly pour water over the sand while mixing to ensure complete saturation. Make sure there is no standing water on top of the sand. If too much water is added, try adding more sand. Place the container on top of the equally sized cylindrical objects. Smooth the surface of the sand and place the building replica on top of the sand in the middle of the container. If repeating the process, it may be helpful to mix up the wet sand before placing the building replica in. Shake and roll the container back and forth and side to side for about 40 seconds. As you've been shaking the container, notice how the sand and rock behave. It's important to note that it looks like the rock is sinking. However, it's really just looking for a new equilibrium point, and once it finds it, it can naturally start to float in the soil. When you're done shaking, you should notice the rock has sunk a few inches into the sand.
We hope that our video was helpful in explaining soil liquefaction. Have fun putting together your own demonstration, and thanks for watching.